In this video, we are going to talk about alkenes and cycloalkenes and how we can recognize these based on formulas using that general molecular formula we introduced in the last video. So alkenes are going to be acyclic, meaning linear or branched, but not in a ring. Unsaturated, so they've got some kind of multiple bond, and alkenes specifically have a carbon-carbon double bond. So that double bond is your functional group. For naming, which we'll do in a later video, our ending is going to be ENE instead of ANE like it was for the alkanes, so it mirrors the name of the functional group. General formula that we introduced, we've got CnH2n, so just twice as many hydrogens. And this only works when you have one carbon-carbon double bond in your molecule. If you have more than one, that general formula is going to have to be different. So two of the simplest alkenes are ethene and propane. So ethene, this is ethene, has two carbons, so that prefix eth is the same as it was for our alkanes. And then ENE tells me that there's a double bond. Here is propene. So prop is the prefix for 3. I do have 3 carbons. And then the ending ENE tells me that there is a double bond. A little bit on geometry. Alkenes, so our simplest one is ethene, 2 carbons. You have to have 2 carbons to have a double bond. The molecule itself is planar, so it's flat. Your carbon, hydrogen, carbon, so the angle here on the end is 120 degrees. For methane, which was the simplest alkane that we had, just a single carbon, the hydrogen-carbon-hydrogen bond angle was 109.5. So we have one fewer atoms on the alkene carbon, so there's more room, giving those bond angles a little bit more space. For cycloalkenes, these are cyclic, meaning the carbons are in a ring, and if they're alkenes, they have to have at least one carbon-carbon double bond. The ones that have only one double bond are going to have the general formula CnH2n minus 2. So this looks the same as it did for alkynes, the 2n minus 2, but now we're losing the 2 extra carbons because we need to remove them to be able to close the ring. So cyclopropane, 3 carbons is the smallest that we can have to have a ring. So they'll look like they are bonded in a triangle. We have to have a double bond somewhere. So then we've got 1 hydrogen on that carbon, 1 hydrogen on this carbon. Down here we'll have 2. So that is C3H4, which does fit the 2n minus 2. So remember, alkane is kind of our starting point, the 2n plus 2. We lose 2 hydrogens for the double bond. We lose another 2 hydrogens to make the ring, which gets us to 2n minus 2. It is possible to have more than one double bond in your ring, especially when your molecules get bigger. So for example, if I had 6 carbon atoms, I could have 2 double bonds. If we fill in hydrogens, this one down here at the bottom. So this is going to be C6H 1, 2, 3, 4, 5, 6, 7, 8. So we should have a CnH2n minus 4 because we went, remember, plus 2 is our starting point for alkanes, minus 2 for one double bond, minus 2 for another double bond, minus 2 for a ring, so that leaves us with minus 4. So C6H8 does fit the 2n minus 4 formula. So hopefully you're starting to recognize how you can figure out how many hydrogens there will be depending on double bond and ring count. The next video we will look at nomenclature. So we'll name our alkenes and cycloalkenes using our IUPAC rules.